In this video, I'm going to show you an example of the chi-square independence test. So I've taken a problem from our homework, and the question is, the table below includes results from a polygraph or a lie detector experiment conducted by researchers. In each case, it's known if the subject lied or did not lie, so the table indicates when the polygraph test was correct. Use a 5% significance level to test the claim that whether a subject lies is independent of the polygraph indication. And then, do the results suggest that polygraphs are more effective in distinguishing between truth and lies? So one of the key words in this problem is the word independent. When you see that word, you might think probability, but by the way the data are set up to us, I just clicked on this little box and it opened up. We see that we have a contingency table. So we have columns of did the subject actually lie, and they know that, no they didn't, and yes they did. And then the rows are the results of the polygraph test. So the polygraph test said that they lied and then that they didn't lie. So our goal is to figure out if what actually happened and what the polygraph test said are independent of one another, so they have no effect on one another, or there is a dependency between the two. So when we go to come up with our hypotheses, we need to include the word independent or not independent. So our hypotheses for this problem are whether the subject lies is independent of the polygraph indication for the null hypothesis, and then the alternative is that they're not independent. So this is not about accuracy, inaccuracy. That is not a technical enough hypotheses. You need to use the word independent, and independent is always your null hypothesis. So in this case, our answer is B. Now the next part of the question is find the chi-square test statistic. So I can get the data into StatCrunch by clicking on the little blue boxes here. Open in StatCrunch. Okay, and then way up here in the corner we have our columns and rows, and I'm going to expand these rows a little bit so that I can read them better. Alright, so the table in StatCrunch gets set up just like the contingency table is written on paper. So you would have to label a couple of rows, you'd label a couple of columns, and then put the 4 values inside of those cells. When it comes to doing the calculations, we're going to go to Stat, Tables. This is a new thing for us. Tables, and then down to Contingency, and then with summary. So I'm choosing with summary because all of our tests from that experiment have been summarized into a table with counts. Now we need to select the columns. So this is the columns that have the data in them, not the words. So the data are in the columns did not lie, and then I need to push Command or Control and then click on lied. Then I tell the computer that the row variables are in this variable that had the little space there. If I go back to the table, it was this first column, it just had a little blank there. So our row labels are in that column. Column label I don't need to do anything with. Group by I don't need to do anything with. Now for the display, I'd like to know the expected count and then contribution to chi-square. So this isn't necessary, but I'm using it for this example so that I can talk about some other stuff later. And then the hypothesis test, I'm doing the chi-square test for independence. This is actually the only test that we'll ever do with a table. Even those two, there are two kind of flavors of chi-square test in this chapter. It's always going to be called a test for independence because that's how we get the results that we want that mathematically match what the chapter is talking about. And then we'll push compute. All right, so let's take a look at this output here. Now let's go straight to the bottom, and this is our chi-square test. So we computed a chi-square test statistic. There's 1 degree of freedom. The way that you can tell there's 1 degree of freedom is take a look at your table, your original table. And I'm going to go back to the data. Here's our original table that had data. If you chop off the last column, and if you chop off the last row, how many cells of numbers are there? Well, if the last row is gone and the last column is gone, or row and column, only the box with the number 17 is left. So there's 1 box, that means there's 1 degree of freedom. That's the fast way how to come up with degrees of freedom. There's also that little formula, row minus 1 multiplied by the number of columns minus 1. That gets you the same place. But chop off a row, chop off a column, how many cells are left? That's your degrees of freedom. And then our next value down here is the test statistic and then our p-value. So our test statistic is quite large, 20.25, and a very small p-value. So like we've learned, the p-value is low, h-naught must go. All right, so 20.25 is our test statistic. Let's go and type this in. 20.25, let's actually check those decimals. 253. 253. All right, we're good. And the p-value says round to 4 decimal places. Let's see, it's less than 0.0001. 0.0001. Let's see how it likes that. It likes that. And then the last part, do the results suggest that the polygraphs are effective in distinguishing between truth and lies? So let's go back to our hypotheses. The null hypothesis says that whether the subject lies is independent of the polygraph test indication. So what does that mean? It means that if the subject is lying, then the polygraph test are going to have no effect on one another. So that's kind of a bad thing, actually. You would hope that the polygraph test would be a result of whether the subject is lying or not. Like it can pick up that the person is lying. So if there's independence, it means that they operate independent of one another. What happens with the polygraph test has no bearing on what the subject did. The alternative, though, is that the subject lies is not independent of the polygraph test. You could think of using the word dependent, but most hypotheses tend to use the word not. So saying not independent instead of dependent tends to be the way to go. So I kind of hope that the alternative is true, because it means that the polygraph test is actually picking up on what's happening with the subject. So what did we get? A large test statistic, a small p-value. The p-value is then supporting the alternative. So do the results suggest that the polygraphs are effective in distinguishing between truth and lies? So since we're rejecting the null hypothesis, there is sufficient evidence, so A and C are going to be our 2 options, to warrant rejection of the claim, warrant rejection of the claim that, let's see, what are the options? That the polygraph testing is 95% accurate. Ooh, I don't know if I like that. We haven't really said anything about accuracy. Let's go down here to C. Warrant rejection of the claim that whether a subject lies is independent of the polygraph test indication. So let's see what C is going to give us. There we go. And we're good. So some more output on that hypothesis test that I chose to get was the expected count and contributions to chi-square. So to actually calculate the chi-square test statistic by hand, I'm going to do that with this output. So we can move some of this around. Let's have some space. Here we go. So I'm going to write out for you how we would compute the chi-square test statistic by hand. And by showing you the contributions to chi-square, the math is already done for me, and the expected counts, that's the middle output here, that is the row total times the column total divided by the grand total. So to get expected counts, we take a row total, multiply by a column total, and divide by a grand total. And because we have 4 cells, you need to do this 4 times. So for that first cell, row 1, column 1, so that's the did not lie and then polygraph indicated lie, our expected count is going to be a row total, 61, multiplied by the column total, so that's 47, divided by the grand total, so that's 102. So we're going to need to do that math. I'm going to go to my calculator right here. Do 61 times 47 divided by 102. And I get 28.10784314. So out to a lot of decimal places. And as our output shows, this middle number here is 28.11. So that is our expected count. You do the same process for the next cell. So for this next row over, we'd have row total, 61, times the column total, which is 55, and divide by 102. So doing that math, we're going to end up with 32.89. So the goal is to compare expected counts with observed counts. So going back to this table here, if I observed 17 people who did not lie, but the polygraph did say that they lied, 17 people fell into that category, but if our null hypothesis is actually true, I should have had 28 people in this category if the null hypothesis is true. So granted, there's going to be some discrepancy between actual data and theoretical data, but is that too far away, or is it close enough? We look at the big picture of all 4 cells. So if I go over to the next row, the next column, I expected to see about 33 people falling into this space of the person actually lied, but the polygraph test said that they lied. Oh, that's a good thing. I expected to see 33 people, but actually there were 44 people there. So this comparison of, how far off is done in a special way with the chi-square test statistic, where we add up observed minus expected, find the difference, square it, and then divide that by your expected count. So because I have 4 cells, I need to do this math 4 times. So I'm going to go through and write out each of the 4 cells math. So I will take my observed. So first cell, I have 17 observed, but I expected to see 28.11 people there. Square that, and then divide that by 28.11. And this sigma here says add up for every cell. So I'm going to plus. Now I go to the next cell. So observed, I saw 44 people in that cell, but I should have seen 32.89 people. Square that, and then divide by 32.89. Now, I always run out of room. There's a lot of math here, so I'm just going to go to the next row. Plus, now there were 30 people in the cell of they did not lie, and the polygraph indicated that they did not lie. But I actually should have seen 18.89 people there. So find the difference, square it, and then divide by 18.89. Plus, now go to the next cell. There are 11 people there. There should have been 22.11. So it looks like there is a little bit of a difference. 22.11. All right. And those 4 calculations, now you have to do them really carefully on your calculator. What I end up doing on my calculator, if you're working by hand here, I would take a parenthesis and then do 11 and then minus 22.11 close parenthesis to the 2, and then here's your division sign, 22.11. So this is what I'm going to end up typing into my calculator. So that's the first piece. Well, actually it's the last piece out of the 4. But that little line of math will give you this part which contributes to the chi-square test statistic. So the last part of this output that I had chosen was contributions to chi-square. We have 4 different pieces to the chi-square test statistic, and that's exactly what these numbers are. So 4.39 is the answer to this piece right here. I'm going to circle it in green, and I'll choose a different color, plus 3.75, that's this piece with the math, plus, what's the next one, 6.53, and then the last piece plus 5.58. And when you add all that together, that gives you your test statistic. Let's go back to it. It was 20.253. Now I know these decimal places aren't agreeing, but because I just rounded the answer from right there. So you have 4 cells, you have 4 contributions to the chi-square test statistic. The larger the contribution, the larger your test statistic, the more likely you are to reject your null hypothesis. So that concludes this video. I did work by hand at the end, but I encourage you to use StatCrunch because it takes a lot of time to do all that math, and there's so many ways to make errors by working by hand that it can get kind of frustrating. So maybe try your work by StatCrunch, and then you can have fun later and then work by hand so you can feel comfortable with both methods of calculation.